All right, so final topic is bond enthalpies. Bond enthalpies are the energy required to break bonds. Note that anytime you break a bond, it takes energy to break a bond. So it's always an endothermic process. And then when you form a bond, that's when you release the energy. That's the exothermic process. Right? So molecules form bonds because they become more stable or lower in delta H. And so this is just another application of Hess's law. So what we're going to do here is that we're just going to pretend you are breaking / forming all the bonds, right? That's not necessarily how it happens in a chemical reaction. All the bonds don't break, only some of them do. But since delta H is a state function, we don't care about what happens in the intermediate steps. We just care about the beginning and the end. In order to think about chemical bond, you have to know some stuff about Lewis structures. So you have to be able to draw your Lewis structures in order to do these types of problems. So if that's something that you're rusty on, definitely check it out. We'll take a look here at the hydrogenation of acetylene. So C2H2 plus 2 H2s is going to go to C2H6. I'm just going to give you the Lewis structures here, but of course you want to be able to make them on your own using the rules that we previously learned. In this case, the C2H2 is this triply bonded carbon-carbon bond. And then of course H2 is just some H's. And then it's going to form C2H6, which is just these carbons bonded together with single hydrogens everywhere. And what we can do is we can look up a table of bond enthalpies. And then again, pretend that we're breaking all the bonds on the reactant side and that we're forming all the bonds on the product side. So here we see that we have a carbon-carbon triple bond. So we'll look at our table, find the carbon-carbon triple bond. It's 837. But since these are bond energies are how much energy it takes to break a bond. Note that it's positive. So actually here we just want to leave it as 837. We're only breaking one of them. And again, this is kind of the opposite of the way it is for the other delta H's where they're a formation. This one is how much energy it takes to break the bond. And then we have two CH bonds. So we can take this 415 and multiply it by 2. And then we've got two HH bonds. They're 436 each. So we're going to multiply that by 2. And again, note that these numbers are positive. It takes energy to break a bond, so we would expect them to be positive. Here, we don't flip the sign here. And then on the product side of things, we've got 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. So again, we're going to use this 415. But this time, we're forming the bonds. That's an exothermic process. We're going to multiply here by -6. And then we form a carbon-carbon bond. Single bond, so that's 345. So minus or plus a -1 times this 345. And then you just sum them all together. And in this case, you get -296 kilojoules, right? So we can tell that overall, this reaction is going to be an exothermic reaction. We got a negative delta H to do this hydrogenation reaction. And we can estimate it because of Hess's law that states basically that enthalpy is a state function. So we don't care how we get there. All we care about is the beginning at the end. Another thing to keep in mind is that these are all just estimates again, especially when it comes to bond enthalpy. The energy of a bond is not just dependent on the bond, but it's dependent on the whole molecule. Remember, we learned that in real molecule quantum dynamics, that the electron is delocalized over the entire molecule. So there really is no such thing as a bond. And so this is just an approximation, but it's still a pretty decent one.